Alrighty, in this video we're going to start Chapter 1, Section 8. And this is the end of Chapter 1. It's just a couple loose ends here. Other types of inequalities. And something we haven't looked at yet are polynomial inequalities, like quadratics, and solving rational inequalities, where we have fractions in there. And of course, always we try to stuff some, or tie some of this stuff into model and solve real-life type problems. This will be a 3-day section. I think day 2 is mostly a lot of calculator work on the TI-89s. So let's dive in. To solve a polynomial inequality such as x squared minus 2x minus 3 is less than 0, you can use the fact that a polynomial can change signs only at its zeros. When we cross the x-axis, so to speak, we change sign from positive to negative or negative to positive, depending on which way we're headed. These zeros are the x values that make the polynomial equal to 0. Between two consecutive 0, a polynomial must be entirely positive or entirely negative. This means that when the real zeros of a polynomial are put in order, they divide the real number line up into intervals in which the polynomial has no sign changes. These zeros are the key numbers of the inequality, and the resulting intervals are the test intervals for that inequality. For instance, the polynomial above factors to this. We looked at this at the top of the paragraph here, x squared minus 2x minus 3. And if we break that down into its two factors, we get x plus 1, and the other factor is x minus 3. So remember, when we were solving these, we would set each factor equal to 0. If x plus 1 is equal to 0, x is negative 1. If x minus 3 is equal to 0, then x is equal to positive 3. These two numbers, negative 1 and 3, are the zeros, and these zeros divide the real number line into these test intervals. If I'm looking at, here's a number line, I know that something's going on at negative 1, and something else is going on at positive 3. And I'm going to use red here to accentuate. These are where we cross the x-axis or change signs from negative to positive or positive to negative. So when we find these zeros, we've chopped our number line up into intervals, depending on how many of these zeros we have. We have 2 zeros, so we're going to go all the way from negative infinity to negative 1 will be our first interval. Negative infinity to negative 1. And then we go from negative 1 to 3, our two numbers that we just found, negative 1 to 3. And then from 3 we head off as far as we can go to the right, and that's all the way to infinity. So we have these 3 test intervals now. So to solve the inequality, x squared minus 2x minus 3 is less than 0, we only need to test a value from each of those intervals to determine if the value satisfies this original inequality. If so, we can conclude that the interval is a solution to the inequality. Let's see what we got here. So if I just took, here are the intervals, broke up here. If I take 0 and I plug it into the original inequality, x squared minus 2x minus 3. If I plug 0 in for x, I'm going to get 0 squared, which is 0, minus 2 times 0, which is 0, minus 3. So I get negative 3 is less than 0. Because remember, our original inequality was set less than 0. Is this a true statement? Is negative 3 less than 0? Yes. So this interval, all the way from negative 1 to 3, is part of our solutions. If, on the other hand, I take a number outside the interval, like negative 3, if I plug negative 3 in for x, I get negative 3 squared is 9. Minus 2 times negative 3 will turn into a plus 6, and then I have the minus 3 at the end. Is that less than 0? Well, no. 9 and 6 is 15. 15 minus 3 is 12. 12 is not less than 0. So all of this is not part of the solution. And if we test the other side, the numbers above 3, you'll see a similar result. They will not make that a true statement. So here are some steps. Finding test intervals for a polynomial. To determine the intervals on which the values of a polynomial are entirely negative or entirely positive, use these steps. First, find all the zeros of the polynomial. Arrange the zeros in increasing order, from smallest to largest. These zeros are the key numbers of the polynomial. Step 2, use those key numbers to determine test intervals. Those key numbers will chop up your number line into intervals. Step 3, choose one representative x value in each interval and evaluate the polynomial at that value. If the value of the polynomial is negative, the polynomial will have negative values for every x value in that interval. If the values of the polynomial are positive, the polynomial will have positive values for all x's in that interval. Okay, let's check these out here in example 1. It says solving a polynomial inequality. Solve this. X squared minus x minus 6 is less than 0. Remember, before we factor, when we were doing these before with equalities, we would set them equal to 0. So we do have it less than 0, so we're all ready to factor. So I need the factors of 6, negative 6, that add up to negative 1. I know my leading term is going to be x squared, so that's x times x. The factors of 6 that add up to negative 1 are going to be a negative 3 and a positive 2. So if I set each of those equal to 0, x minus 3 equals 0 means x equals 3. And x plus 2 equals 0 means x is negative 2. So those are the key numbers, or the critical numbers. I like the word critical numbers better. That'll get you ready for a topic in calculus. Critical numbers. These are where important stuff is happening on the graph at positive 3 and negative 2. So here, I should have used a more blank number line, but at negative 2, something's going on, and at positive 3, something's going on. So now I have 3 intervals, and I'm going to write those right in here in this column. My first interval goes from all the way on the left, negative infinity. Ooh, that's a terrible infinity. Negative infinity to negative 2. And where this interval leaves off, the next one picks up, negative 2 to positive 3, our other test number, or another critical number. And then from there we finish off, and we go from 3 to positive infinity. So what we want to do now is pick an x value, a test number somewhere in that interval, and try it out in our polynomial. And let me do this. Oops, no, I don't want to do that yet. There's 2 ways we can test it. We have our original polynomial, x squared minus x minus 6 is less than 0. Or you can look at it in its factored form. X minus 3 times x plus 2 is less than 0. So let's pick a test number. Between negative 2 and infinity, let's just pick negative 3, a number just inside there. It doesn't matter what x value we pick. So what's the value of the polynomial going to be? We can take the negative 3 and we could plug it in here and see what happens. We could find the actual number, the output. Remember, we're only concerned with positive or negative. So an easier way to do this most of the time is to plug that x value into these factors. So let's see, if I plug negative 3 in here, I get negative 3 minus 3, that's a negative 6, or just negative, that's all I'm worried about. If I plug the negative 3 in for this x, negative 3 plus 2 is also a negative answer, a negative 1. A negative times a negative is a positive. Is a positive less than 0? Let me write in here positive. So what's our conclusion is this is not part of the solution set. Not part of solution. On the next one here. In between negative 2 and 3, if I ever have an interval where 0's in there, I always like to use 0. That's an easy one to work with. Let me get these out of here. If I plug 0 in for x now, I'm going to get 0 minus 3. That's a negative 3. If I plug 0 in for this x, I get 0 plus 2 is a positive 2. A positive times a negative is a negative. Is a negative number less than 0? Yes, it is. So this is part of the solution set. The last interval, 3 to infinity. I'll pick a number just outside. Let's say 4. If I plug 4, well, let's plug it into the original inequality to try it up here. If I plug a 4 in here, I get 4 squared is 16 minus x, and x again is 4, and then minus 6. 16 minus 4 times 6 is 16 minus 10, or 6. Is 6 less than 0? No. We got a positive answer. A positive number is never less than 0, so this is not part of the solution. So when we come down here to our intervals, we know that from negative infinity to negative 2 is not part of the solution, but from negative 2 to 3 was. So I'm going to really color this in with blue here. And then when we went from 3 to infinity, that was also not part of the solution set. So the only numbers that will work and make our inequality a true statement are the numbers between negative 2 and 3. Now, there's also another way to look at this to sort of check it. The more math we know, the better, and especially if we know the basic shapes of graphs, we know we can figure some stuff out. If I come back to here. Now, we're looking at a one-dimensional number line. Remember, we can also think about the Cartesian plane, the xy coordinate system. If I throw a y-axis in here, let's see what happens. So here's my y-axis. Or polynomial, we did this earlier in the year. What is the general shape of a squared term, or a squared polynomial? This is a quadratic. What general shape does it have? Remember, if it is a positive x squared, it's a parabola opening up. If it is a negative x squared, it's a parabola opening down. When we first started this problem, we factored it, and we got x plus 2 and x minus 3, and we found the zeros of the polynomial. On the number line, that was what chopped up our intervals. Those are also the points where our polynomial, or our parabola, will cross the x-axis. If we know it crosses the x-axis here and here, and we know it is a positive x squared, which means a parabola opening up, our parabola is going to look something like this. It has to. Now, if we go back to the original inequality, it says less than 0. Where does this parabola have negative y values? Where are we under the x-axis? Well, the only spot we dip under the x-axis is between the negative 2 and the 3, because all of these values here would hit the negative part of the y-axis. We cross at the zeros at 3 and negative 2. After that, we are now positive. We're now greater than 0, which would make that a false statement. So we know that over here is not part of the solution, as is all the numbers here to the left of negative 2. They are not going to make this a true inequality. Only the spots here where we're under the x-axis are going to work. So that's just sort of like a little shortcut. The better you know the basic shapes of graphs and how they behave, the easier it is to figure this stuff out, or at least to verify and check the answer that you found to make sure that it's reasonable. And that's sort of summed up here. As with linear inequalities, you can check the reasonableness of a solution by substituting x values into the original inequality. For instance, to check the solution found in example 1, try substituting several x values from the interval negative 2 to 3 into the inequality. X squared minus x minus 6 is less than 0. Regardless of the x value you choose, the inequality should be satisfied. It should be true. You can also use a graph to check the result in your example. Sketch a graph of y equals x squared minus x minus 6, as shown down here in the figure. Notice that the graph is below the x-axis from the interval negative 2 to 3. In example 1, the polynomial inequality was given in the general form, with the polynomial on one side and the 0 on the other. Whenever this is not the case, you should begin the solution process by writing the inequality in general form. Like here. Let's see what we got. And now it's not just a squared. It's a cubic. We got to the third power. Solve. 2x to the third minus 3x squared minus 32x is greater than negative 48. Well, to get the ball rolling, we want to have a 0 on the other side. So I'm going to add 48 to both sides. 2x to the third minus 3x squared minus 32x plus 48 is equal to 0. Now, I can't remember how they show you how to factor this in the book. Easiest thing to do would just be to factor this on one of our TI-89 calculators. And if you do that, we're going to get three factors. First one is x minus 4, and then we get x plus 4. And our last one is 2x minus 3. That would be the tough one to find on our own. And we have greater than, I should have had a greater than sign there, greater than 0. So if we set each of these separately equal to 0, here we're going to get x equals positive 4. For the next factor, x equals negative 4. And when we set this equal to 0, we're going to add 3 to both sides and then divide by 2. So we're going to have a 3 divided by 2. X is 3 halves. So let's write those in ascending order. The smallest, of course, is going to be negative 4. And then we're going to have 3 halves. That's 1 1/2. And then we're going to have positive 4. Oops. So I'm thinking here about a number line. I'll squeeze in a number line here at the bottom. And again, we were only worried about the relevant stuff. So let's say negative 4 would be about here. 3 halves, we'll put that about here, 1.5. And then positive 4 we'll put about here. So we have broken up the number line into intervals. 1, 2, 3, 4 intervals we're going to have to test this time. So our first interval is going to go from, of course, negative infinity until we get to negative 4. And then from negative 4 to 3 halves. And then from 3 halves to positive 4. And then we'll finish up by going from 4 all the way to infinity. So there's our 4 intervals, test intervals. And we want to plug in a test value. Between negative infinity and negative 4 is a negative 5. If I take that negative 5, let's see here, this might be easier if we test these in the factored form. Remember, we're only worried about positive or negative, not the actual value. So if I plug negative 5 in here, negative 5 minus 4 is a negative number. Negative 5 plus 4 is a negative number. And here we'd have 2 times negative 5. That would be a negative 10. And we minus some more, so that would also be negative. A negative times a negative is a positive. Times another negative is a negative answer. So here our polynomial value is negative. And we want to be greater than 0. Is a negative number greater than 0? No. So this is not part of the solution. Alrighty. Next interval, negative 4 to 3 halves. In between there somewhere is 0, and I love working with 0. So 0 minus 4, that would be negative. 0 plus 4 is positive. 2 times 0 is 0, minus 3 is negative. So we're going to have a negative times a positive is negative, and a negative times another negative is positive. So here on this interval, we are positive. Is a positive number greater than 0? Yes. So this is going to be part of our solution. Alrighty. Next interval, from 3 halves to 4. Good number in there is 2. If I plug a 2 in for this x, 2 minus 4 is negative. 2 plus 4 is positive. And in this last piece, 2 times 2 is 4, minus 3 is positive. So a negative times a positive is negative, and a negative times another positive is still negative. Is a negative number greater than 0? No, it's not going to be part of the solution. Negative, not part of the solution. The last one. Between 4 and infinity, you can pick any number. I just picked 5. 5 minus 4, that's positive 1. 5 plus 4, that's also positive, positive 9, but the number doesn't really matter. 2 times 5 is 10. 10 minus 3 is positive. So positive times positive is positive. Is a positive number greater than 0? You bet it is. So that is going to be part of the solution. So let's color in the graph. The first interval was not part of the solution. So over here from the left of negative 4, we're not going to do anything. But from 4 to 3 halves, we're going to have that as part of our solution set. So I'm going to color that part in. From 3 halves to 4, we found out was not part of the solution set, so we're going to leave that alone. And then from 4 to infinity is part of our solution. So from 4 here, we're going to head over, and that is the rest of our solution set. And I don't know if later in the slideshow I have a good picture of that graph, but we can sort of back that up. You know, the parabola one was much easier. Parabola shapes are easy to come up with. This one is a little different. This was a cubic, third power. And if it is a positive third power, we're going to go, in general, up to the right, down to the left. So if I take that from this graph, down here would be headed off to the left. And I know over here, we're going to be headed up to the right. So let's see if the graph fits the rest of it. So we're going to come up, and we're going to be positive until we cross the x-axis again. Now we're negative, so we're no longer part of the solution set. We're going to dip down here until we cross again at 4, and then we're back up to the positive part. So roughly, that's what the graph is, the general shape is going to be. And okay, from this you can conclude the inequality is satisfied on these intervals, from negative 4 to 3 halves, and from 4 to infinity. So if we wanted to write it in union or the set notation here, from negative 4 to 3 halves, from 4 to infinity, and we are unioning those together. We're combining them together for our overall set. Ooh, and here they do show the different test values that we used. I think those are the same ones I did. Yes. Alrighty, a couple practice problems for the team huddle. So pause the video. This one is already set less than 0, so factor it and come up with your test intervals and test them out. This one, of course, address the negative 3 first, and then come up with your number line and figure out where the solution set lies. Oops. Okay, so for the first one, let me get this one out of the way so we have a little more space to work with. Solve the inequality, graph it on the real number line. Again, we have our 0 there, so if we factor, we're going to have, of course, x and x. Factors a negative 3 that add up to positive 2. That's going to be a plus 3 and a minus 1. So that is going to chop up our number line. So if we set this equal to 0, we're going to get x is negative 3. So let me put my negative 3 right about here. If we set x minus 1 equal to 0, we'll get x is positive 1. So we've now figured out our intervals, and we just want to test those out. And remember here, this is less than 0. We're looking for negatives. If this is negative, it's part of the solution set. So let's see here to the left of negative 3. Let's just test, I guess, negative 5 would be good. If I plug a negative 5 in for this x, negative 5 plus 3 is a negative answer. Negative 5 minus 1 is a negative 6. Negative times negative is positive. Is positive less than 0? No. So this is not going to be part of our solution set over here. But let's check from negative 3 to positive 1. I like 0, of course. 0 plus 3 is positive. 0 minus 1 is negative. A positive times a negative is negative. Is a negative number less than 0? Yes. So this is going to be part of our solution set. And then from 1 to infinity, pick any number you want. Let's say 5. 5 plus 3 is positive 8. 5 minus 1 is a positive 4. Positive times positive is positive, and that is not less than 0. So over here is not part of our solution set. And an easier way to get that, or a way to just check our answer, is this is a positive x squared. So we know it is a parabola opening up, and we already know its x-intercepts. So, we would have a parabola looking like this. We want less than 0. Where does the parabola dip below the x-axis? Just here between -3 and +1. Ooh, and this would be a neat way to point out also, what if we had flipped the inequality? What if it was x squared plus 2x minus 3 is greater than 0? Well, then that would just flip our solutions around. You know, here, our parabola is under the x-axis, so that's where it is negative. We want positive. Where is it greater than 0? Well, for that, our solution set would be from 1 to infinity, because here our parabola is above the x-axis, and from -3 to -infinity, because again our parabola has gone from being below the x-axis to above. So flipping that inequality changed our solution sets. This was part of the solution set, now it is no longer. And the other pieces that were not part of the original solution set now are. Alrighty. 27. Let's see here. If we move the 3 over and make it positive, we now have x to the third minus 3x squared minus x plus 3 is greater than 0. I guess if you're doing this at home, we don't have a real good way to factor that until we do Chapter 3, Section 3, which is coming up. The factors we're going to get here are going to be x minus 3, x plus 1, and x minus 1 greater than 0. So if you didn't solve this problem yet because you were stuck on the factoring, there are the factors. You know, pause the video and keep going. So let's see here now, if we set each of these equal to 0, x minus 3 equals 0 means x is 3. X plus 1 equals 0 means x is -1. X minus 1 equals 0 means x is +1. So there's how we chop up our intervals. The lowest of those is -1. So that's going to be our one on the most left. And then we have +1. And then our last one is +3. Put that about here. Oop, I didn't want to erase all of that, because we can use this to test our intervals out nicely. Okay. Our first interval will be less than -1, or from -infinity to -1. A good number in there, I guess we could use -2. If I plug in -2, -2 minus 3 is a negative number. -2 plus 1 is also a negative number. -2 minus 1 is another negative. Negative times negative is positive, times negative is negative. Is a negative number greater than 0? No. So this is not going to be part of our solution set. In between -1 and 1 is my favorite number, 0. Plug it in. 0 minus 3 is negative. 0 plus 1 is positive. 0 minus 1 is negative. Negative times positive is negative, times another negative is positive. Is a positive number greater than 0? Why, yes, it is. So this is going to be part of our solution set. And now, between 1 and 3, use a 2. 2 minus 3 is negative. 2 plus 1 is positive. 2 minus 1 is positive. Negative times positive is negative. Negative times that positive is negative. Is a negative number greater than 0? No. So this is not part of the solution set. Last number of interest is at 3, so let's pick a number above that, say 4. 4 minus 3, that's positive. 4 plus 1 is positive. 4 minus 1 is positive. Positives all multiply to a positive. Is a positive number greater than 0? Yes, it is. So this is going to be part of our solution set. And there we go. Again, a rough idea of the graph, x to the third goes down to the right and up to the left. So we know we're down here starting on the left, and we're going to cross. And we're going to be above. Greater than 0 means we have solutions. And then we cross again, and now that we're negative, the solution set stops. We're under the x-axis, and we cross again, and we're up off to the right toward infinity. Alrighty, good stuff. Homework. Page 185, 13 to 16. Number 22 is the tough one. Factor that on the TI-89 calculator.